Here I introduce clustering SDF, self-organized neural implicit surfaces for 3D decomposition. This work is done by Tianhao Wu, Chuanxia Zheng, Qianyi Wu, and Tenzhen Chen from Nanyang Technological University, University of Oxford, and Monash University. Given a set of RGB images, as well as the corresponding 2D segments from an off-the-shelf model, clustering SDF reconstructs the surface of the scene while fusing these inconsistent segments to be coherent and more accurate in a 3D space. As for the motivation of designing clustering SDF, first, there exists disconnection between segmentation and 3D reconstruction in current nerve-based methods. The embedding features for semantic and instance rendering are derived from independent MLPs that do not necessarily correlate with the underlying RGB or depths. While for SDF-based methods, they perform better regarding the geometry accuracy because the segmentation results have a direct impact on the final rendering. However, they require multi-view consistent labels for reconstruction and decomposition. Therefore, we have clustering SDF. Given inconsistent machine-generated 2D labels, the 360-degree segmentation results are consistent in 3D. Also, as built upon object compositional neural implicit surface representation, clustering SDF maintains the capability of reconstructing the surfaces of individual objects in the scene. Compared with the state-of-the-art methods, our clustering SDF achieves very competitive results against previous 3D segmentation methods. And also, it can be noticed that clustering SDF can segment tiny objects better than the baseline models, for example, the pillow on the sofa. Also, our segmentation results are consistent across multiple views. The segmentation results of clustering SDF are closer to the actual geometry of the objects. Here, the areas to be noticed are marked by the red boxes. To demonstrate the effectiveness of clustering SDF, we trained the model and contrasted lift for less than 10% of the complete training time. And the results show that our clustering SDF can achieve sharp semantic and instance segmentation at a very early stage. Now let's move on to the design of clustering SDF. Clustering SDF samples rays from single 2D segment maps and split them into n groups corresponding to distinct 2D labels. Each ray is then processed to obtain the SDF representation. Here we adopt an important perspective that, after softmax normalization across different SDF channels, they can instead be considered as probability distributions that assign each ray to different instance categories with different probabilities. The differentiation loss then leverages normalized SDF distributions for individual objects and keeps the clustering centers apart. We present them by different colors, and the darker colors denote higher probabilities for the same channel. Furthermore, we also have a one-hot loss that encourages the predicted distributions to be in the one-hot format. It should be noted that, compared with the traditional contrastive loss, the clustering loss does not use each positive or negative pixel pair, but only the clustering centers, thus reducing the complexity significantly. To learn more, please check our paper. Thank you.